Hello, my name is Jonas Gonzales. I am a PhD student at the Italian Institute of Technology. Today, I will present you our work on a bio-inspired architecture for autonomous transfer learning for object detection. Deep learning has revolutionized object detection, reaching state-of-the-art performances and continues to improve years after years. New architectures with increased accuracy and faster inference times allow to exploit these deep networks in real time in robotics platform, smartphone, and computer. But to achieve state-of-the-art performances, independently of the model, it is mandatory to have data, a lot of data. Without this large dataset containing millions of annotated images, such as COCO or ImageNet, none of the presented networks would have reached state-of-the-art performances. But collecting and annotating such amount of image is time-consuming, as it is done by humans, and has to be repeated for new class or object in new environment. Moreover, when applying this model to robotics, an issue arises: how to deal with the changing environment and new object the robot will encounter. While performing well on benchmark dataset, deep learning models suffer a drop of performance when applied to robotic platforms, mainly due to the environment robots are deploying, which was not represented in the training dataset. Robots, due to hardware, space limitation, and the requirement to run on real time, usually cannot use high-resolution camera, which are not the standard in benchmark dataset. All these factors put constraints for the deployment of deep learning in robotics and require a new approach to deal with this limitation. Deep learning algorithm works well as long as the data they are trained on is representative of the final task. Robots, thanks to their different sensors such as cameras, microphones, and even tactile sensors, can acquire a huge amount of data which could be used to train those networks. Moreover, robots being physically present in the world can act and interact with the environment, giving a variety in the data they can acquire, which is useful for deep learning approach to generalize. While robots can have access theoretically to infinite data, they miss a way to learn from them in an autonomous way. More specifically, when considering a supervised learning approach, they need a way to label those data. The challenge is then to propose new technique to format and process the data coming from the robot sensor to use them in a supervised learning approach. That is, a way to autonomously annotate the data of the robot sensors. In this work, we propose to address this challenge by taking inspiration on how babies learn using facilitation mechanisms such as visual attention or active vision to propose a computational framework that can automatically process the raw data of the robot sensors and process them to perform supervised learning. We took advantage of transfer learning approach where deep networks trained on big dataset can be used as generic feature extractor to reduce the training time to adapt to new scenarios and objects. We humans learn through interaction with the world, and robots being embodied could follow a similar learning path. To learn, we use facilitation strategy like visual attention, which allow us to focus on a particular point, retaining only the most salient information. This process, coupled with active vision, gives a facilitation mechanism to perform complex tasks like segmentation, as not all the visual information is used, but only a part. Humanoid robots can reproduce this behavior, facilitating the processing of the information coming from the sensor. For example, by selectively look one object at a time, this allows to break down a complex scene into several simple parts, which can be used to create a dataset for learning. We integrated this idea into a unified computational framework, which allows the iCub robot to explore the scene as a human could do using a visual attention mechanism and active vision. The visual attention module is used to guide the focus of the robot on silent region of the input image, which is then used as a proxy for the stereo vision pipeline. By retaining only a part of the information, this facilitates the segmentation of the object from the background. Once the object is segmented, the robot can track it, which gives a collection of data points that can be used to create a dataset. We tested our computational framework in a natural and ecological interaction where the iCub robot is in front of objects randomly disposed in a table while interacting with a human partner. Using our framework, the robot can explore autonomously the set of objects displayed in front of him, collecting meaningful data that can be used to train a deep network for object localization. The first step in our framework is the attention module, which is used by the robot to explore the scene in an autonomous way. As you can see from the image, the visual attention focuses on silent parts of the input image, as for example the ball. This allows the robot to trigger an ocular movement towards the point of interest and put the focus on this region of the image, which is used to facilitate the segmentation process. The second step in our architecture is a vergence mechanism that takes the point of focus from the attention module and align the region centered on this point at same location on both images, as you can see in the steric image on the top. We then compute a zero disparity map, which is used to segment the object from the background, as you can see on the middle figure. This process allows to extract only the relevant information from the initial point of focus, here the ball, discarding the other information. Using the attention module used to only focus on a part of the image, facilitating the segmentation process. All this pipeline is inspired by the vision system of human, where binocular movements help to focus and segment the object from the background. Finally, the last part of our framework is to use the extract template from the segmentation process to let the robot perform object tracking and collect data points of the object in the autonomous way. As it could happen in an interaction between infant and the parent, the human partner shows the object to the robot, which can track the object and save the image and the associated bounding box, collecting meaningful data points relative to the initial attended object. Following our pipeline allows the robot to create a labeled dataset in an autonomous way, which we use in a transfer learning fashion. We use pre-trained network on big datasets such as COCO or ImageNet and reuse the early layers as generic feature extractor and only retrain the top of the network, the last layer as represented in red in this figure. This reduces the training time and the amount of data needed while keeping high accuracy. On a small GPU, it took around 1 hour to retrain the network until convergence. Running our framework took the robot around 10 minutes to collect the dataset, with an average of 700 images for each class. We chose to test our framework with 5 objects that were already present in the COCO dataset to compare the performances of the network before and after retraining. We chose 3 middle-sized objects, the ball, the peluche, and the book, and more challenging objects, the bottle and the cup. As you can see from sample of the training set, our approach worked well for big objects like the ball or the peluche, but produced bad data point for small objects with too much background, like for the bottle. To test our architecture with the autonomously gathered dataset, we created a test set with 5 new instances for each object present in the training set with a different background. We computed the mean average precision with an intersection of union of 50% for both models before and after retraining. We achieved an improvement of 30% with the faster RCNN network and only 4% with the SSD model. The poor increase of accuracy with the SSD model can be explained by the fact that we didn't fine-tune the hyperparameters. For example, it is well known that choosing carefully the set of ensures is a crucial parameter for SSD architecture, which could have improved the gain of accuracy. The reason we choose not to fine-tune the hyperparameters and keep the default one was to propose an autonomous pipeline where no human supervision was required. So to conclude, in this work we wanted to propose an architecture that allowed the iCub robot to explore autonomously a scene and learn to detect this object. We integrated visual attention and active vision and showed that it can be successful to guide the learning of the robot and explore the scene by identifying all the salient regions, in our case all the different objects, and collect a suitable dataset that can be used in a transfer learning approach to retrain a deep object localization network. With this work, we think that this could be a solution for one limitation of deep learning, that is the need of annotated data when we need to adapt to new object and environment. We are aware about the limitation of our architecture, especially with the failure to produce good data for small objects. To cope with this issue, we will in the future improve our segmentation mechanism to take into account other features such as color or texture. This work was also for us a validation step toward a more complex architecture to develop a system to perform long-life learning with robotic platform. While in this work we consider only one interaction and use generic label, we want to extend this architecture to perform continual learning for object detection. The idea is to use a joint attention mechanism where the human interact naturally with the robot and give the word associated with an object that can be used into an autoencoder to extract a latent representation which can be then used as a label for the object. It will also be useful as the latent representation can be used by the decoder network to reproduce the audio and thus allow the robot to pronounce the name of the object. In social interaction, the detection of faces is an important vector of information that individuals use every day in society. Faces guide our social interaction and allow us to get important information such as the age, sex, understand other emotion, and even help us in speech recognition. The ability to detect and focus on faces is crucial to engage in social interaction, and it is therefore a fundamental skill for robots. But how does human learn to detect faces? Neuroscientists and psychologists have been investigating how babies learn to detect faces, and it has been shown that they rely on innate mechanisms that guide the development of a specific brain area. To replicate naturalistic interaction as they could happen with baby, we create a game-like scenario where people had to find iCub's favorite objects. People needed to attract the robot attention and then find iCub's favorite object to make it happy. The purpose of having a game-like scenario was to demonstrate the importance of the low-level attentional mechanism to direct the robot focus on faces as it could happen with babies. This is the point of view from iCub cameras. The two attentional mechanisms were integrated into a single silency map. As illustrated in this example, the combination of auditory and visual attention converge toward the faces. This is not a priori encoded. The robot autonomously focuses on the face as it is the region with the maximum silency, because while attracting the robot attention, people naturally call him and move hand to make the robot gaze at them. When the attentional module converged toward a stable point of interest, the divergence mechanism was used to align the focus at the same location on both cameras. This process is inspired by the way the human focuses on objects and helps to perform segmentation. The silent region exhibits zero disparity, whereas the rest of the scene usually doesn't. And this particularity helps to segment the region from the background, as you can see on the video. At this point, the robot was able to track the participant faces. It also exhibited a side face to emphasize the need to find the robot's favorite object. From the video, you can see that participants present objects to the robot while he was tracking their faces and collecting data. The interest of having a natural scenario is also to produce a diversity of data, as sometimes people were covering partially their faces while presenting the object to the robot and moving to take the object. To test our trained network, we first built our own test set. We recorded video from the iCub cameras during a public visit to our laboratory and annotated manually the images of visitor faces. We choose to test our system with scenarios that the robot will normally encounter, as meeting people in our laboratory environment. The test set was composed of 150 data points chosen randomly from the recording. We compare our model with the Viola and Joyce face detection algorithm as baseline. We compute the mean average precision with 50% intersection of union to evaluate our model and achieve a score of 48%. As the network sometimes recognizes not only the faces but also part of the upper body, as you can see on these samples, we relax the intersection of union to 40% and get a map score of 63%. In both cases, our network outperformed the baseline algorithm. While the trained network doesn't reach state-of-the-art performance when compared to other deep networks, these results are encouraging because we show that it is possible to use bio-inspired processes to guide the learning of robots. The data gathered automatically during a game-like interaction can be used to train a deep network that successfully learns to detect faces and generalize to new scenarios. Finally, this process doesn't require human supervision, so it can be run for a longer period of time to collect more and more evidences to improve the performances. We think that making robots learning as baby does from their environment and interacting with others is important to develop more autonomous robots. Moreover, allowing robots to learn from their experiences can be a solution for the need of consequent amount of data to train deep network. Thank you for your attention. You can find here our group of research and learn more about our project.